Good morning to all. I am A.Subashini, Assistant Professor, PG and Research Department of Chemistry, Sithalakshmi Ramaswamy College, Tiruchirappalli. Today, I am going to discuss supramolecular chemistry. Supramolecular chemistry is a highly interdisciplinary field of science covering areas such as chemical science, physical science, life science, engineering science, polymer chemistry, and material science. Supramolecular chemistry is considered as molecular assemblies rather than molecules themselves. In 1967, Charles Pedersen observed that crown ethers showed molecular recognition. Donald J. Cram established the term host-guest chemistry, where the host molecule can accommodate another guest molecule. In 1978, Jean-Marie Lehn coined the term supramolecular chemistry. Together, Pedersen, Cram, and Lehn received the Nobel Prize for Chemistry in the year 1987. Crystal engineering, design of solids with desired physical and chemical properties. According to Desiraju, the understanding of intermolecular interactions in the context of crystal packing and in the utilization of such understanding in the design of new solids with desired physical and chemical properties. Basic introduction of supramolecular chemistry. Traditional chemistry, that is conventional chemistry, deals with breaking and making of bonds, that is covalent bonds. Supramolecular chemistry defined by phrases such as chemistry beyond the molecule, that is the chemistry of intermolecular assemblies and of intermolecular bond. The main objective of supramolecular chemistry is to design and develop novel functional systems by joining multiple chemical components through non-covalent interactions. Supramolecular chemistry as a discipline which is now being explored in various areas such as drug development, sensor catalysis, nanoscience, molecular devices, etc. Supramolecular chemistry focus on non-covalent interactions such as electrostatic interactions, hydrogen bonding, pi-pi stacking interactions, halogen bonding, hydrophobic interactions, and van der Waals forces. Under electrostatic interactions, we are going to discuss ion-ion interactions, ion-dipole interactions, dipole-dipole interactions, and metal-ligand coordination. Electrostatic interactions occur between charged molecules. An attractive force is observed between oppositely charged molecules and a repulsive force between molecules with the same type of charges. The magnitude of this interaction is relatively large compared to other non-covalent interactions. Electrostatic interactions, ion-ion interactions. Ion-ion interactions observed in ionic cubic lattice of sodium chloride, in which each sodium cation is surrounded by 6 chloride anions. The sodium cation is able to organize 6 complementary donor atoms about itself in order to maximize non-covalent ion-ion interactions. Dipole-dipole interactions. When polar molecules are attracted towards ions, example NaCl dissolved in water, the negative end of the dipole is attracted towards the positive cation, while the positive end of the dipole attracted towards the negative end. Dipole-dipole interactions are observed in organic carbonyl molecules. When polar molecules are brought nearer to each other, they orient themselves. The positive end of one dipole attracts the negative end of another dipole and vice versa. Here, two carbonyl molecules are arranged in linear fashion. Two such carbonyl groups are arranged in opposite direction, forming a dipole-dipole type of interactions. Metal-ligand coordination. Metal-ligand coordinations are highly directional and specific. This type of interaction occurs between metal ligand and electron-rich atoms and is of moderate strength. Hydrogen bonding. A hydrogen bond is an interaction between a proton donor group DH and a proton acceptor A. The DHA interaction being called as hydrogen bond. The atom to which the hydrogen atom is more tightly linked is called the donor, whereas the other atom is called the acceptor, which has a partial negative charge. Hydrogen bonds are commonly written DHA and usually involve a hydrogen atom attached to an electronegative atom such as oxygen or nitrogen as the donor, and similarly electronegative atom often bearing a lone pair as the acceptor A. Usually, a hydrogen bond can be characterized as a proton shared by two lone electron pairs. Hydrogen bond ranges about 15 to 40 kilocalories per mole for strong hydrogen bonds, 4 to 15 kilocalories per mole for moderate hydrogen bonds, and 1 to 4 kilocalories per mole for weak hydrogen bonds. The van der Waals cutoff criterion requires that in a hydrogen bond, the distance between H and A must be smaller than the sum of the van der Waals radii of H and A. Here, OHO, OHN and FHN are examples for strong hydrogen bonds, and its energy is about 15 to 40 kilocalories per mole. NHN and NHO are examples for moderate hydrogen bond, and its range lies from 4 to 15 kilocalories per mole. CH pi and CHO interactions are examples for weak type of interactions, and its bond energy is 1 to 4 kilocalories per mole. Types of hydrogen bonds. Hydrogen bonds are classified into two types. Hydrogen bond formed between two or more neighboring molecules are called intermolecular hydrogen bond, and it leads to association. Examples: para-nitrobenzoic acid, para-hydroxybenzoic acid, ammonia, water, hydrofluoric acid, etc. Hydrogen bond formed between two different atoms in the same molecule is called as intramolecular hydrogen bond, and it leads to chelation. Examples: salicylaldehyde, salicylic acid, etc. Intermolecular hydrogen bond is stronger than intramolecular hydrogen bonding and van der Waals forces. Hydrogen bonding play a key role during molecular recognition. Hydrogen bonding occurs only when the functional groups that are interacting are properly oriented. Lessons from nature: DNA bound by base pairs. Nature has evolved functional assemblies over millions of years. Hence, scientists often gather inspiration from the beautiful structures that are encountered. E.W. Major. This is double helical structure of DNA. Base pairing takes place between a purine and pyrimidine molecules. In DNA, adenine and thymine are complementary base pairs and cytosine and guanine are complementary base pairs. Bases adenine and thymine are held together by two hydrogen bonds, that is one NHN and one NHO hydrogen bonds. Bases guanine and cytosine are bonded together by three hydrogen bonds, that is two NHO and one NHN hydrogen bonds. In this double helix structure, guanine forms triple hydrogen bonds with cytosine and adenine forms double hydrogen bond with thymine. Here, adenine and guanine are doubly ringed structure. Thymine and cytosine are singly ringed structures. DNA is essential for inheritance, coding of proteins, and providing instructions for life and its processes. Self-assembly in nature, hydrogen bonds in DNA are responsible for specific base pair formation in the DNA double helix and a major factor to the stability of DNA double helix structure. Naturally occurring DNA, perhaps the best known self-assembling structure in biological systems, exists in a double helical form. The two single strands are held together by number of hydrogen bonds involving acidic hydrogen atom, that is hydrogen bonding donor, oxygen hydrogen bonding acceptor, and a nitrogen atom of the purine and pyrimidine bases to maintain the double helical structure. Significance of hydrogen bonding. Physical state of water. Hydrogen atom is located between two different oxygen atoms of the neighboring molecule. Without hydrogen bonding, water would have exist as a gas like hydrogen sulfide. In that case, no life would have been possible without water. Pi interactions. Pi interactions are classified into four types: pi-pi stacking interactions, cation pi interactions, anion pi interactions, and polar pi interactions. Pi-pi interactions. It is observed between aromatic rings and these sometimes provide important contribution to molecular recognition. When the aromatic rings face each other, the overlap of pi electron orbitals results in an energetic gain, that is pi-pi stacking gives additional stability to the molecule. There are two main types of pi interactions: face to face and edge to face. Face to face pi interactions are responsible for the slippery feel of graphite and its useful lubricant properties. Similar pi stacking interactions between the aryl rings of nucleobase pairs also help to stabilize DNA double helix. Edge-to-face interactions are responsible for the characteristic herringbone packing in the crystal structures of a range of small aromatic hydrocarbons including benzene. Here, the centroid to centroid distance is found to be 3.5 angstrom. This is face-to-face interaction, and here we can observe edge-to-face type of interactions. Cation pi interactions. Cation pi interactions are observed in transition metal cations such as iron 2+, platinum 2+, etc. are well known to form complexes with olefinic and aromatic hydrocarbons such as Zeiss salt and ferrocene. The bonding in such complexes is strong and could by no means be considered non-covalent, since it is intimately linked with the partially occupied d orbitals of the metal. Cation pi interactions, ferrocene. Here iron 2 plus is sandwiched between two aromatic cloud of cyclopentadiene. Here platinum adopts for coordination. The three sites are occupied by chlorine atom and the fourth coordination site is occupied by double bond of ethylene molecule. Some simple models. Cation pi interactions. Cation pi interaction is observed between benzene ring and a sodium cation. Polar pi interactions. Polar pi interactions is observed between water molecule and the benzene ring. Next one, pi-pi stacking interactions. Pi-pi stacking interactions is observed between electron-rich benzene ring and an electron-poor hexafluorobenzene molecule. The van der Waals interactions. Van der Waals interactions are weaker, short-lived and less specific than those described above, but it is undoubtedly important because this interaction generally applies to all kinds of atoms, molecules and ions when they are sufficiently close to each other. It is driven by interactions of dipoles created by instantaneous unbalanced electrical charge distributions in neutral substances. Unusual intermolecular forces, halogen bonding. Halogen bonding is attractive non-covalent interaction that can form between an electrophilic region of a halogen atom in a molecule and a nucleophilic region of the molecule. Here 2,1,4-dioxane molecule is bridged by bromine molecule. Figure A represents conventional halogen bond and it is observed between a pyridine molecule and iodobenzene. Type 2 halogen-halogen bond. The difference between B and C are the aromatic rings are somewhat perpendicular to each other. In C, the two aromatic rings are parallel to each other. The bonding can be exploited in areas such as supramolecular chemistry, crystal engineering and the fabrication of liquid crystals. Hydrophobic interactions in an aqueous medium plays a very important role. It is the major driving force for hydrophobic molecules to aggregate in an aqueous medium as seen in the formation of a cell membrane from lipid-based components. The tendency of nonpolar molecule in a polar solvent to interact with one another. The nonpolar substances like fat molecules tend to clump up together rather than distributing itself in a water medium because this allows the fat molecules to have minimum contact with water. Molecular recognition. Molecular recognition is the specific interaction between two or more molecules which exhibit molecular complementarity through non-covalent interaction. Molecular recognition has drawn much attention with regard to separation chemistry. One of the promising approaches to create molecular recognition materials is the molecular imprinting method. Such a phenomenon is of crucial importance in the areas of molecular biology, crystal engineering and supramolecular assembly. Supramolecular chemistry can be split into two categories: host-guest interactions, self-assembly. Host-guest interactions encompasses that the ideas of molecular recognition, that is the interactions through non-covalent bonding. The non-covalent bonding is crucial in maintaining the three-dimensional structure of large molecules such as proteins and is involved in many biological systems. Host-guest interactions. Host-guest interactions are observed in complexes that are composed of two or more molecules or ions that are held together through non-covalent interactions. Here the host is represented by channel-like structure and the guest is represented by blue-like ball-like structure. Molecular recognition and complexation. A suitable guest molecule is recognized and form a host guest molecule. Complementarity. The host must have a binding site which can recognize to guest molecule and form host guest complex. Receptor analyte or host guest affinity is nature inspired and at the heart of many biological processes such as enzyme substrate antigen antibody interactions. There are two important terminology used in complementarity: electronic complementarity and size complementarity. Electronic complementarity. Negative host binds with positive guest or the positive host binds with negative guest. Next, size complementarity. A host must contain a correct size of binding site which can easily fitted to guest to form host-guest complex. A supramolecule is a well-defined distinct system generally through interactions between a molecule, receptor or host having convergent binding site such as donor atoms, sites for the formation of hydrogen bonds and sizable cavity, and another molecule, analyte or guest having the divergent binding site such as hydrogen bond acceptor atom. Self-assembly. The process by which a supramolecular assembly forms is called molecular self-assembly. Some try to distinguish self-assembly as the process by which individual molecules form the defined aggregate. Self-organization then is the process by which those aggregates create high-order structures. Molecular self-assembly is a process in which molecules spontaneously form ordered aggregates and involves no human intervention. The interactions involved are usually non-covalent. Supramolecular chemistry finds applications in catalysis, sensing, metal extraction, medicine, green chemistry, molecular devices, materials technology, etc. Thank you.